Okay, let us come to the torque equation of our DC machine. In the previous video, we tried to produce the voltage equation, and we came to know that the induced voltage in our DC machine is going to be K phi n, where K phi is ZDP by 16A, and we said that our induced voltage depend on these three parameters: machine constant, flux, and the speed. And now let us try to generate the torque equation, or try to show the torque equation in our DC machine. So similar to the voltage, for the torque in a DC machine to be produced, three things again they are required: the flux in the machine, the armature current in the machine, and constant speed. I mean constant depending on the construction of the machine. So these three things: the machine constant, which is K, the armature current, and flux. These things are very important. Now to just formulate the torque equation, the torque on the machine of a real DC machine is equal to number of conductor times the torque on each conductor. Here, the torque in our DC machine, torque induced in our DC machine, we can say torque induced in our DC machine, it depends on the number of conductor or DC machine times torque in each or on each conductor of the machine. Each conductor, that is the total induced torque in our DC machine. But what is the torque on each and every of our conductor? Torque in our single conductor. So the torque in any single conductor under pole phase was produced previously that RLB, RLIB. It depends on this. What is that? IRB. Let me come here. But this torque on each conductor, it's going to be RLB. It says RLBI of the conductor divided by A. That is what it says for each conductor here. RLIB, sorry, this was not there. IRLB of our conductor. So what is I of our conductor again? What is I conductor? Look, our induced torque in our machine, it is going to be number of turn of the number of conductor in the machine times torque of each conductor in the machine. But the torque on each or single conductor in the machine, the torque on each single conductor in the machine, it is RLB times IL of the conductor, current inside the conductor. Current inside the conductor. But what is the current inside the conductor? What is current inside the conductor? It is going to be the total armature current divided by total armature current, or I can say okay, not to confuse with the paths. So total armature current divided by the number of paths, current paths. So if you substitute this inside this, we'll get this relation. So torque in a single conductor is going to be RLB divided by A. Just substitute this inside this, putting this inside this. So that is torque on the conductor. So if you replace again, put this equation, I conductor is IA by M, and Z is obviously the total conductor. Then torque induced in our machine is going to be ZRLBIA by A. Just substituting here. So T conductor, let me show you here. Now let me erase this. Therefore our induced torque in our machine, it is going to be Z times torque on each conductor, we said, and torque in each conductor now to become IA LB, this is L, length of the conductor, divided by A. Let me rewrite this. This is L, the length of the conductor. So this is the overall induced torque in our machine. Similar with the previous, we can rewrite it. Previously, what we said when we generate the voltage equation, we said that flux inside our machine is going to be 2 pi RL B by A, we said. Just rewrite this similar with the previous thing. Rewriting in terms of the flux. So if you write this induced torque in terms of the flux, it is going to be ZdP, 2 pi A times flux times I. When we say normally I, 2 pi RLB, here IA was remaining normally. No, sorry. And here IA was remaining. IA is there, no? Sorry again. Oh my god, sorry. Let me rewrite. So induced torque is going to be Z RLB IA divided by A, we said, the overall. And if we rewrite in terms of the flux, which is 2 pi RLB by P, this was the flux, then induced torque is going to be Z pi, ZP, not pi. So ZP 2 pi A times flux times IA. Just rewriting in terms of the flux. So our induced voltage is going to be, torque, sorry, our torque is going to be ZP 2 pi A phi by N, and this is, we said that it is K. Therefore induced torque is going to be K times pi IA, which is already written at the last. Here it is everything in there. So the induced torque in our machine, what we usually call it, torque equation of our DC machine, is going to be K phi IA, where K is going to be ZdP 2 pi A. This is the torque equation of our DC machine. Now, from both the induced torque and the induced voltage we generated previously, both of the equations, the internal generated voltage and the induced torque equation given, are only approximation. They cannot be exact. Why they are approximation? Because not all the conductors in the machine are under the pole phase at any given time, and also because the surface of each pole do not cover the entire per pole, 1 by P means entire per pole of the rotor surface. It means that all the conductor surface, they cannot be under the entire pole of the machine. there should be some slot, some winding which can be beyond the pole. So at that time, this equation they may not consider. That's why we said it is called approximation. It is approximation. To achieve the greater accuracy, exact induced voltage and the torque, the number of conductor under the pole face could be used instead of total number of conductor on the rotor. See, we have to use exact number of conductor under the pole. At that time, the generated equation is going to be exact, like that. Let us continue. Having said, now we generated the voltage equation of our DC machine and torque equation of our DC machine. Let us come to the concept called back EMF or counter electromagnetic force. Now till we're talking about generated voltage, induced voltage normally. In truly speaking, this induced or generated voltage holds true for the generator, because that's the one which is inducing or generating voltage. When we come to the motor, the correct term we usually have to use is the back or counter EMF. Why we named it is, see, it has seen that when current carrying is supplied to the armature conductor placed in the main magnetic field, torque is developed and the armature rotates. When we place, by motoring action it means, when we place a conductor, current carrying conductor inside the magnetic field, we experience a force, we say, and torque, the torque. So the armature will. Simultaneously, the moment we place, not only the force, voltage also get induced inside the conductor. When the armature conductors cut across the magnetic field and an EMF is induced in these conductors also. Two things are happening inside these machines. We are placing current carrying conductor inside the magnetic field and it produces rotation. It produces motion. When the moment the armature starts rotating inside the magnetic field, it also induces that voltage. Now, if it is a generator, we are directly interested with the induced voltage. Now, in case of the motor, torque is created. Now, the motor is rotating. Even though we don't want that induced voltage, but it is inevitable to get induced voltage inside the motor. We call that back EMF. Of course, we need this back EMF. It has very significant important. We will come to it later. So it can be seen that the direction of this induced EMF is opposed to the applied voltage. There is a person called Lenz law. Lenz law is the name of a person. He investigated that, according to him, of course, it was coming from the Faraday's law. What he said, electromagnetic induction states that the direction of the current in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field which produces it. What does this mean? See, when we supply the voltage, current is flowing through the coil. When we place the current carrying conductor inside the magnetic field, it creates a torque, we said. So the current which is produced inside this coil and they create the torque, it produces its own flux. So that flux is going to be a counter of the flux which is produced by induced EMF, back EMF. That is an opposite. So Faraday, he indicates that opposition with a minus sign. We usually keep the formula when you write the induced voltage minus d phi by dt. Of course, n we can, when we want to consider for any number of conductors, we can put n here. Anyhow, this minus indicates that it is produced by the anti-flux produced by the main flux, anti or opposite direction. We call this, it is called back or counter EMF in a motor, special in a DC motor we call it a back or counter EMF. So from the equations, voltage equation we produced previously, we said simply E induced. Now when we talk in a motor, it is usually has to be back or counter EMF. Now we named it EB, and the equation is the same, nothing is changed. The equation is the same. The equation is the same. So if you see this equation, and let me show you here, and the induced we said, now we will call it back EMF. It is going to be K phi N, back EMF. So if you see the flux, I mean the speed of the motor, if you see the speed of the motor, now solve for N, it is going to be EB. Of course I can keep this K phi. See, this is a machine constant. This is a machine constant. So what it says now, the speed of the motor, it is inversely proportional to the flux and directly proportional to the back EMF. Directly proportional. That's what it says. So the speed of the motor is showing that is directly proportional to the back EMF and inversely proportional to the speed, that show this relation. So back EMF is always less than the applied voltage, though this difference is small when the motor is running under the normal condition. It's always less than the applied voltage, obviously. Let us see just this one practical example. Now this is shunt DC motor type. It is a shunt DC motor type normally. So when the DC voltage is applied to this terminal across the motor, so the field windings are excited and the armature conductor are supplied with the current. So since they are parallelly connected, immediately IA and I shunt start flowing. Therefore driving torque acts on the armature, which begin to rotate. It starts rotating. As the armature rotates, as the armature starts rotating, back EMF is induced, which opposes the applied voltage according to Lenz's law. So the applied voltage has to force a current through the armature against the back EMF. It has to force. It has to force this voltage. The applied voltage should defeat this EB, or should be greater than EB, so that the current will start flowing through the armature. It has to follow the armature. Here, this is V is there applied, and the EB, internal back EMF, is there. When this V is greater than EB, so that IA will flow inside the machine. It's flow inside the machine. Therefore, the electric work done in overcoming and causing the current to flow against EB is converted into mechanical energy developed in the armature. Now work is going to be done in energy conversion here. Therefore energy conversion in DC motor is only possible due to the production of back EMF. If we don't have EMF, that energy conversion will not happen. There is no position between V and EB. So EB is required to produce the work get done. That work get done is the one which is producing mechanical energy conversion. So net voltage across the machine is going to be the difference of the two. It means V minus EB, the net force inside the machine. The net voltage, not force, inside the machine is going to be the difference of the two. Now from this circuit equation, if you write KVL for this circuit equation, the shunt motor, it is going to be EB plus IRA, what we usually call voltage equation of DC motor. This. So it is going to be VBIM. If you solve for IA, armature current, from this, so V minus IB divided by RA, which is this one, this relation, see, V minus IB RA. And normally V and RA are fixed. We'll give fixed supply, and this RA is not going to be changed for a machine, so they are usually fixed. So the value of EB will determine the current. So this current value will determine on this EB, it means that is the only factor which is deciding this IA, because these are fixed. So if the speed of the motor is high, for example, when the back EMF is large, and hence the motor will draw less armature current and vice versa. It means if the speed of the motor increase, see what is back EMF? You said that the back EMF is the back EMF is this one. If I increase the speed of the motor, let me use different pen. If I increase the speed of the motor, back EMF will increase. So from the voltage equation mentioned here, IA, what it says? It is V minus EB divided by RA. Now if EB increase means current will increase, armature current will increase. So armature current increase means the motor will draw high currents and vice versa. It depends on the armature current. So the back EMF is large, and hence the motor will draw less current. It means here, sorry, if this is increasing, obviously, I'm sorry here, if V minus EB, now if this speed increase, EB increase. If EB increase, V minus, so armature is going to decrease, not increasing. It's going to decrease. Okay, EB will, IA will get decrease. So that IA decrease means the motor will get slowed down, it says. Let us see a little bit in depth what is the significance of back EMF. What is the significance? Its importance. The presence of back EMF makes the DC motor self-regulating machine. Self-regulate. How? It makes the motor to draw much armature current as is just sufficient to develop the torque. This is similar to what I'm saying now. It depends. This armature current, it depends on EB. It depends on EB. When EB is increasing, IA is get decreasing. See, it says here, when the mechanical load supplied on the motor increase, if the load increase, obviously its speed will get decreased. Load increase means speed will get decreased. Speed decrease means it reduces EB. Speed decrease means it get reduced. If EB get reduced, this VI by V is going to be increasing. EB increase means V minus IB also increase this difference. If this some difference increase means IA is getting increased, obviously. Hence the motor draws extra current. It draws extra current IA from the main. Thus the back EMF regulates input power as per the extra load. So as the load increase and decrease, IA will get increase and decrease. That control over the motor operation was happening due to the existence of back EMF. The existence of back EMF. And when the motor is running on no load condition, what happens if load is not there? A small torque is required for that, to just simply overcome friction and the windage losses. Therefore armature current I is very small, and the back EMF is nearly equal to the applied voltage. These two are almost equal to the applied voltage, because we need very small current at no load condition. That is the advantage of back EMF. Here is the detail what I said previously, just one by one case. If the motor is suddenly loaded, the first effect is to cause armature to slow down. If the motor is suddenly loaded, the armature will slow down. Armature slow down means the speed of the armature, the speed at which the armature conductor moves through the field is reducing, and hence speed reduced means back EMF fall down. Back EMF reduced means it allow large currents, large current, because V minus EB is going to be large, so IA is going to be large. IA large means the current draws high current and it increase the driving torque of the motor. IA increase means it increase the torque, because we said torque is going to be K phi I A. IA means the torque. IA increase means torque increase. Thus the driving torque increases as the motor slows down. So the motor will slow down when the armature current is just sufficient to produce the increased torque required by the load. It balances according to the change of the load. The torque of the motor will be regulated. That was happening through back EMF. So it has a big advantage in a motor. If the motor decrease, the vice versa of what I said, if the motor decrease, the driving torque is momentarily in excess. Just at that instant is going to be excess for that small torque. So the armature accelerates. As the armature speed increase, back EMF got increased. Back EMF increased means it causes the current to decrease, because V minus IB is going to be less. So V minus IB means it's less armature current. So less armature current means the motor will stop accelerating. It start decreasing when the armature current is just sufficient to produce the reduced torque required by the load. Therefore, that back EMF in a DC motor regulate the flow of armature current, and it is automatically change the armature current to meet the load required. That is the importance of the back EMF. Thank you very much for listening.